That's small. Okay, incremental is a functor. Modeling incremental processes with Monoidal categories. Dan Shiebler?
Shiebler, yeah.
Shiebler. Okay, good. Go for it.
All right. Hi, everybody. I'm Dan. I'm going to talk about incrementality as functor. So I'm going to go over a couple of things. We're going to just start with some background. All right. So formal grammars. These are family of constructs that are basically various ways to slice up the concept of having a subset of some free monoid that we accept as a language. So basically we have this notion of some set of alphabet or vocabulary, and some subset of that is accepted. So these are like the grammatical sentences in some family of possible sentences that you could form with words. And so grammars, the formal grammars can vary in their complexity, from very simple formal grammars like regular grammars, regular languages, all the way up to Turing machines, recursively enumerable grammars, and even unrestricted grammars. And so the various mathematical structures that we can utilize to characterize these different grammars and recognize them based on some sort of algorithm that can determine whether or not a string of characters or a string of words is grammatical or is not grammatical is a pretty deep field of study. But what we're going to go over right now is some of the ways that we can represent these sorts of things with category theory, and with monoidal categories in particular. So pregroups are this construct that is useful for representing certain kinds of formal grammars. And you can also think of it as an algebraic structure that lies somewhere in between a monoid and a group. So essentially, rather than having the invertibility condition of a group, we enforce a pre-ordering, and we have, or a partial ordering, depending on where there's actually different definitions of it. And you replace invertibility with this right and left adjoints. So just to make that concrete. So rather than each element in a pre-group having an inverse, each element has a right adjoint and a left adjoint that such that these inequalities or relations are satisfied.
So pre-groups built over a partial order then?
Yes.
Okay.
Yeah. Yeah, we can basically think of it as a partial order equipped with the adjoints.
Okay.
So with this monoidal product. And so the difference between a pre-group and a proto-group is just that pre-groups have these expansions where you have the unit having this less than or equal to these pairs relation, where proto-group does not.
Pre-groups are done by Landbeck. Who did proto-groups?
I think also Landbeck. So the motivation is you can actually, when you characterize formal languages in pre-groups, you can actually characterize them all with proto-groups as well. You don't need the expansions. So sometimes the expansions make things more complicated, but they make a lot of the proofs easier, so we keep them.
Now, I'm just wondering, do you have, maybe because there's a little more time here, example of why one needs this rather than just, the adjoint rather than on the nodes in the group?
Yeah, so I don't have like a great example for this, but the intuition is when you have, if you're going to, it's a little easier to describe the intuition after we kind of go into the language.
Sure.
But,
well, whatever point is.
But I just, when you have like some object in a sentence get used multiple times, so you need to bridge different parts of a sentence, like this do or these kind of transition words, sometimes it could be useful to have these kinds of expansions to connect things together.
Okay.
I'm not really like a formal grammars person, so I wish I could explain that better.
Yeah, no, it's all right. Just a natural question why you need pre-group rather than just group.
No, great question. So this is basically how we can relate these notions of pre-groups to what we start thinking about as language. So essentially, let's say we want to start parsing these to start parsing a sentence of words. So we're going to associate each word with a type in the pregroup. So these are, so here we have a set of atomic types that get combined with the monoidal product. And we're going to associate each word with some type and some string of types connected by monoidal product in the pregroup. And so the kind of punchline here is that we're going to call a string of words grammatical when we have this pregroup relation relating it to the sentence type. So our sentence, John likes Mary, is grammatical because when we associate each of the words with the pregroup type, stick them together, and then apply our pregroup relations, we get this relationship. So it's worth noting that these pregroups have the same expressive power as context-free grammars, and it shouldn't be too hard to see why that's the case. In the context-free grammar, we kind of expand our rules in a context-free local sense. Similarly, in pregroups, we are locally reducing elements that are right next to each other. So there's kind of a mapping there. And so it's a relatively rich framework within which we can express some nice ideas. This is more of an example.
If you were to specialize of a particular type of context-free grammar, namely regular grammars,
Yes.
so what type of, what would fall out? It would be a group? Would it become a group? Specialized?
So you're saying if we had if we wanted
It
to,
would be a linear grammar.
yeah, if we wanted to build an algebraic structure similar to pregroups that had the same expressive power as regular grammars rather than having the same expressive power of context-free.
Yeah.
I mean, the issue is we could have these like infinite, arbitrary size expansions that a regular grammar can't necessarily capture. It's a very interesting question. I haven't thought about that at all. So we can sort of squint our eyes and think about these sorts of things as monoidal categories when we kind of step away from the algebraic perspective and look at the categorical perspective. We just have the simple mapping from pregroups to monoidal categories. We have our monoidal product and we have arrows. Everything kind of looks very nice. And so for those of you who are string diagram people, when we do this, our string diagrams look a lot like syntax trees, the type of parse trees we might get when we're parsing things with a formal grammar. And in a parsing library, we get, if we draw the string diagrams for the arrows in the pregroup grammars from our string of types to the sentence type. All right, so one of the things that we've done in this work is try to expand this to a more general class of grammatical constructions, and then also try to formalize the notion of the relationship between the vocabulary and the actual rules in the grammar. And we've called this monoidal grammars. So here's just some definitions. A monoidal signature is like your template for a monoidal, free monoidal category. You're probably all familiar with this sort of thing. So we have just our set of arrows and their domains and codomains, and we can build a free monoidal category from that. If we want to start having more complex relationships, where we're not just building free monoidal categories, we're building monoidal categories with different sorts of relations or equating arrows, we can represent it with a monoidal presentation, which is essentially just a monoidal signature along with a relation that says which arrows are the same. So this is just another way of representing a monoidal category that will be a little bit more convenient for the
Okay, so it's not just a monoidal category. It's a monoidal category with duality. You don't have symmetry because word order matters.
Yeah.
So, but you have duality. You have closure.
I don't think you need closure.
But so every element has a left adjoint and a left.
So in the case of pregroups.
Right.
But that's not specified in this, right?
Yeah, this is not just for pregroups. This is more.
We're
The-
Right,
the
so
Nodal
this is a
signature.
more general thing.
Yeah, we're
Yeah,
not
this
talking
is
about
more
any
general.
equivalent of that yet.
Okay.
So, can you do something, as we're gonna take, if you've got time,
Yeah.
let's just, when you go back to signature, let me just understand this really hands-on.
Yeah.
So I've got a set of generating objects.
Yeah.
And the free monoid over that is just lists of that set. So what are these arrows doing in this monoidal category? They're just, it's sort of like an underlying graph, and then we're just gonna freely.
Yeah,
so it's a
that's
free
exactly
that's
what
what I
it
mean,
is.
it's the free monoidal category over a graph as opposed to.
Yeah, no, that's exactly what it is.
Well,
The monoidal signature is basically a graph, and then your free monoidal category is your transitive closure.
Yeah, I mean, pointing out, you can have like a formal product of your generators as like the source and target of your arrows, so you don't
Yeah.
have to just have arrows directly between generating objects.
Sure.
Yep.
Right, and then when you go to a presentation, that's because the resultant category might not be thin, right? The resultant and so this lets you specify when.
Yes, then you can have more complex relationships where you don't just collapse every arrow into the same one.
Oh, I see, so in the free one, you assume everything is thin.
No.
Oh, the opposite.
It's
Yeah.
you get that for free. The fact that everything is thin.
Okay, but then when you move to the presentation, then you're explicitly collapsing stuff.
No, that's not right. I'm sorry, I
Yeah.
misspoke. You're right. It's the opposite.
Okay.
You assume that every composition is unique in
Yeah.
the free monoidal category. In the presentation, you start to equate arrows
Okay.
based on the relation. That was right. I misspoke.
Okay, thank you.
Okay, so it's just an alternative representation. So a monoidal grammar, basically we want to have the same notion that we were discussing earlier, where we can have these arrows from strings of types to the sentence type be a parsing, be a representation of something being grammatical. But we want also to have a relationship between words and types, because as we'd seen earlier, some words are unit types, some words are monoidal products of types. And we want to be able to expand to more complex rules and such. So basically we have this notion of a monoidal grammar, which is very close to this slice category, where we just are defining these mappings into our objects from the union of our words and a sentence type. The difference, based on the difference between this definition and that category exactly, is just that this slice mapping needs to map into the individual objects rather than tensor products of objects, which is why it's a subcategory rather than the category itself. And so this is the notion of a monoidal grammar that's kind of a generalization of the pre-group construction that I described earlier.
Yeah, I'm sorry, what did you say? It's almost, what's missing from being a slice category?
Oh, it is a subcategory of that slice category. If I want to formulate this as a slice category, I would need to. Well, I guess it's not a slice category exactly. It's a good question. We've thought of it as a subcategory of the slice category, because basically the slice category, then you have to throw out a number of the slices, because you can't have any ones where the elements of that set are getting mapped to composite objects. It's only the ones that are getting mapped to individual objects. So I'm not sure if you'd formulate that as a slice category over a different category. I'm not sure if it's possible.
If you went to context-sensitive grammars, you wouldn't worry about that? Because the rules in context-sensitive grammars have many things going to many things. Or regular.
It's not about the rules here, it's about the vocabulary. The idea here is I'm trying to pick out objects that are going to represent my words and objects that are going to represent my sentence. And so the picking out of these things is where I want to have, if I want to have this equivalence where I'm representing things as this finite presentation with the vocabulary, then this kind of maps to this subcategory.
Is there any reason actually that S would need to be a possible composite object, or?
So me and my co-author discussed that. I thought there's not a reason, and he thought there was a reason, and I do not know exactly why he thought there was a reason.
Gave in.
Yeah.
You don't have to start with an S, because it would just be, if you don't start with an S, you would have an empty language, right? So one of the...
you could have an S that nothing maps to. That would be an empty language.
Or leave out the S.
Yes. That we could leave out. You could define this so that we could leave out the S. That I don't think that breaks it if the S is optional. That's a good question.
Yeah, I mean, it sounds like the usual thing, right, where you just get different things depending on what I call my final setting.
Yeah, I think the notion is basically if you start from the presentation definition and then define the category that comes out of it, this is kind of the category that we get. It's this subcategory. If we wanted to define things starting from the categorical perspective, we could be a little bit more creative and pointing things around. This is sort of the succinct explanation that is in the language of presentations.
Is it right to call V a finite vocabulary, not a finite variable? The V's are the variables, no? In the grammar.
The V's are vocabulary.
They're
they represent words.
Yeah.
Okay.
Yeah, it's our set of words.
Okay, good. Sorry.
So this is, just what a morphism looks like in a slice category. I don't think there's really anything else on here. This is just kind of a picture of it. So we have these presentation homomorphisms, which are just our functors, our Monoidal functors, where we have this commuting condition. So here's just an example for pre-group grammars in the language of the presentation. So we have our vocabulary being our words, our objects being our types and the adjoints, our arrows being our sort of our adjoint relations, and then our relations that we're quotienting over being the snake equations for the relationship between the associativity and such. Okay, so just some vocabulary that I'm going to use later. So parse state is just an arrow from this tensor of word objects to any object. A parsing is an arrow from the tensor of word objects to the sentence object. And then the language is just our set of sentences, tensors of word objects that have at least one parsing. So some nice things here are these parsings are their associated string diagrams are parse trees. Our parse states we can kind of think about as, because this is going to get into incrementality in a moment of how these parse states get built up into parsings in an incremental fashion. So we can kind of think about them as a parse tree that's not fully built yet. We start with our set of tensor products and we start applying arrows. And we haven't applied all of the arrows yet, but we have this partially built parse tree. All right. So basically, this is kind of the key problem is what happens when we start thinking about how this relates to speech, where words come one at a time. If we think about, if I say like the first 3 or 4 words of a sentence, that may not form a full parsing yet, but I may be able to say something about the structure of what I've spoken by looking at the possible parse states.
Or at least you haven't made a grammatical blunder yet.
Yeah, that is true. I still have potential to make a grammatical blunder or potential to not. So we can think of our parse state as our syntactic understanding of the way what I've spoken, how it's structured, and our new word should evolve this understanding of syntax. So we have an action of the free monoid on the category of endofunctors here, the free monoid of our vocabulary. So basically, if we have a new word, this kind of in a very, very simple fashion defines an endofunctor over our monoidal grammar category. We have basically just it maps any object to that object tensored with the word, it maps any arrow to that arrow tensored with the ID. The identity arrow for this word. So this is a very kind of not informative endofunctor where this is sort of the dumbest approach, like, okay, this is what a new word does to our parse states. But it doesn't really tell us how this parse state can evolve. So ideally we can capture all of the ways this understanding can evolve in the face of a new word. And so the way we do that is we define this mapping, which looks very strange and weird right now, but I'm going to relate it to something that makes a lot more sense in a moment. But just to kind of categorize exactly what this is doing, we're essentially trying to capture how our system might evolve once a new word is introduced. So what this is a mapping from an arrow to all of the arrows that we can express as the tensor of our some other arrow in our grammar composed with the tensor of the original arrow tensored with the identity. So basically any arrow that we can factor back to our original parse states and the new word added. So this is like all of the possible parse states. So assuming that we fix our understanding of the first half of my sentence, what are all the possible understandings that we can get afterwards? And so once we add this new word.
Right, and basically, well, in fact, and that tensor ID thing says that yes, any transformations I could have done with the word things so far are still valid, no matter what I'll add later.
Yeah, exactly.
Kind of the locality principle that it works.
Yeah.
No matter what the unknowns are that may come later.
So something that's kind of interesting here is that we're basically saying that we can't change the way we've interpreted what we've already heard. So we're saying that based on our parse state and based on what we've interpreted thus far. And so first, this is not a realistic model of speech, and so we're going to introduce non-determinism in a moment, so to kind of gloss over the way that works, and to make it so that assumption doesn't hurt us. But this is just the way this mapping is working is in a deterministic fashion. Like assuming that we fix our understanding of what I've said thus far, how can we understand once we've added this new word? So we're going to relate this back now to automata, and I'll kind of describe piece by piece how this is going to work. So we're going to take a quick digression into description of automata. So they're a simple model of how a system can evolve with new information, so we can see how this is going to be useful in our discussions of how parse states can evolve in the face of new words. And so this is a very basic automata that it accepts a sequence of words, and it's sort of this, we can think about this as this set of states and transitions, and at each time we see a word, we transition our state. So we begin at Q0 if we see so here words are letters. So if we see B, we transition to Q0. We see C, we transition to Q1. We see C again, we transition back to Q1. We see A, we transition to Q2. And basically if we have some sequence of words or tokens or whatever, we can say that this sequence is accepted or rejected based on the final state. So automata are a nice way of kind of describing the different ways that we can parse languages. They're another model of grammars. A finite automata represents regular languages, and an infinite automata can represent any language. But they're just a nice way of representing states and transitions.
Yeah. Right, in particular now, a finite automata without stacks.
Yes, that's right. You need some, if you want to go beyond regular languages, you need some way to handle infinity.
Right. But in a controlled way.
Yeah.
Not just throwing in.
Well, not necessarily. If you want arbitrary grammars, you can just.
Then you can go arbitrarily. Sure. Yeah, you can go arbitrary infinity.
Yeah.
Exactly.
Well, yeah.
So, deterministic and non-deterministic automata. Deterministic automata, we're saying that each transition is uniquely determined. Non-deterministic, we're saying not necessarily. So there's a lot of different characterizations of non-deterministic automata that are at various levels of rigorous and easy to understand. And you can kind of think of them as we're tracking the set of possible states that we can be in at each time. There's also this notion of transitions that don't involve inputs, but we'll gloss over that.
Well, in particular, in your thing with the middle node Q1, YC, and A, I can either go back to Q1 or move on.
Yeah, exactly. We see A, and so generally what we do is we assume that we can we're going to be non-deterministic. We're non-deterministically at Q1 or Q2 or both. And so we can, these things sometimes can be a lot easier to represent as just, rather than the states and arrows, sometimes it's easier to think about these things just as functions. So a deterministic automaton is our set of states. It's a pair of functions. One function accepts a set of states and a element of our vocabulary and returns the state that we're transitioning to. The other function maps our states to whether or not they're an accept state or not. So the B here is the booleans. A non-deterministic automaton is the same thing, except we're just saying that our function now can map it to the power set of states rather than just
So in order
single state.
or are we saying a relation rather than a function?
Well, it needs to be, it can't be a partial function though, because it needs to be total.
Sure.
Wait, but can it map things to the empty set? Or,
Not usually.
Well,
okay.
That's a good, that's a good question. There's a,
I mean,
Yeah,
you can do it that way. It's just not conventional in automated theory.
Yeah, I mean, here we are doing it that way. So I guess in that case you can think of it just as a relation. That's a good
well,
point.
just saying you got stuck, so I couldn't accept the thing.
Yeah,
It's just saying I got stuck, it didn't make sense, I give up. This isn't a sentence.
yeah.
Mathematically, I mean, it just formally is.
Yeah.
Yeah, so I mean we're going to define a functor into automata, and then the image of that functor is not going to include any automata that have this behavior.
Okay.
But that is a that is in the the codomain, but it is not in the image, I guess. Function terminology.
Or maybe you can fix it by any another state saying, when that happens, when it gets stuck, I just go in this other stuff.
Yeah, I mean, you could probably characterize it that way if you start.
I mean, that's the usual thing. Is
Yeah.
you just have an extra state to hold all of the things that don't have anywhere else to go.
Yeah. Good. Right. Okay, so back to Wstar, which maps our word and parse states to all the parse states that factor into our original parse states. Basically, the punchline here is that Wstar looks a lot like a non-deterministic automata transition function. Which basically is. We're mapping our pair of an arrow and our new word into the power set of arrows, into a set of arrows. So there's this notion now of we have Wstar. This is a construct based on the innards of our monoidal grammar. Can we now uniquely define automata for a monoidal grammar that models its incremental structure? And so the way that we formalize this is with coalgebra. You could probably formalize this without involving coalgebra, but it's a lot cleaner this way. And I'm not totally sure how we do that. So coalgebra is just a really nice, clean way to talk about dynamical systems in a formal fashion, just in terms of signatures and implementations. So for those of you who are not familiar with the coalgebra of the functors, so we're working with endofunctors over set. So if I use set terminology, everything that we're going to be talking about is just coalgebras of endofunctors over set. So it's a pair of a function and a set, where our function maps that set into some other set f of x. So if our functor is the identity functor, then coalgebras are just functions from a set into itself. So this could be a permutation, this could be the constant function that maps everything to one element. So this is just an image of what a coalgebra of the identity functor would look like. And so we can represent deterministic automata and non-deterministic automata as coalgebras of these functors. So for a deterministic automata, we're mapping each, it's this, a implementation, a deterministic automata is a function that accepts an element of the state and maps to this pair of a Boolean and a function from our vocabulary into the set of states. So we're basically just pivoting the equations that I showed a second ago here into the language of coalgebras and functors. And since we're working with endofunctors over set, this all works out very nicely and cleanly to be exactly the same thing. All right, so we can define a functor, which we call I, or the incremental functor, from the category of monoidal grammars to coalgebras of the non-deterministic automata functor. The proof of this is pretty simple. The only thing is you need to show that our monoidal grammar functors correspond to coalgebra homomorphisms. We have a paper we're going to be publishing on this that has the proof in it, but it's not very long. It's pretty easy to show it. You just have to kind of go piece by piece. But this is kind of nice because sometimes it's easier to think about these sorts of things in terms of automata, and monoidal grammars are pretty general, and this provides a nice relationship that lets us talk about some interesting things. So to give an example, so this is just our monoidal grammars mapped to automata. Our functors between monoidal grammars are mapped to coalgebra homomorphisms. So this is just what I said a second ago. Just to give an example of some of the interesting things this can kind of let us start to do. So bisimulations between automata are this sort of common notion that we use. We talk about the co-induction and such, and when we're talking about whether or not automata behave the same way. And we can say that if monoidal grammar categories have functors between them, corresponding...
Any old functors?
Yeah.
So a functor between two monoidal grammar categories has to be really strong, right?
Couldn't
I define some really bad functors, or like?
Yeah. So this is because of the structure of. This is because of a few things. So it's because of the structure of the automata themselves, and it's because of the structure of the slice categories corresponding to the monoidal grammars.
So what that's saying is that most of the power of the automata arises from something that has not a lot to do with the underlying monoidal grammar category, right?
Yeah. So I think what part of this says to me is that a reverse construction, a functor that goes in the opposite direction, will tell us a lot about how this construction, what information exactly this construction is providing to us about the automata.
Like, I can produce a really trivial monoidal grammar category, right? Like,
Yeah.
like sort of like a terminal-ish one or something, right?
Yep.
And I can probably make functors to and from it for most other categories.
No, because if you have a terminal category that makes like all the words go to the same place, then that won't have functors most other places because it won't preserve.
Not even like embeddings or, like, I mean, that's what I'm saying, is either functors are really powerful, and to have a functor at all means that you've got to share a lot of structure. But, you know, functors between any old category that's not a monoidal grammar category can be
The other thing is
pretty
that
arbitrary, right?
it could be that the bisimulation of automata itself is just not a very useful construct when we're thinking about
Right, but you see what I'm getting at, right?
Yeah, no, I can totally see what you're getting at
You
here.
could probably come up with a pretty degenerate example.
Yeah, so I think that there is I honestly I haven't thought about the degree to which we could build trivial functors between these, and that is definitely a good point.
They correspond to any trivial clouds for homomorphism? So if you have
Yeah, so the
a homomorphism, there won't be one that's interesting.
But it gives you, but bisimulation is a very powerful property.
yeah.
I mean, you have to remember that S is an important thing here too.
I think another thing here is that when we're working with non-deterministic automata, bisimulation is a less powerful property, less interesting.
Okay.
Which is another reason why I think a mapping in the opposite direction will be really useful here.
Right, so you only have a functor going one way or two functor, right, the category of.
Yeah, so right now
Actually,
we
that's another question. I mean, you said you have a functor from, the big functor.
Yeah.
From grammars to automata, or
Yeah.
gadget that you call automata. But that's gotta be a two functor, right? Grammars
because
are
we're
already categories.
yeah. I'm not sure I follow. I don't doubt it, but I'm not sure where why that's immediately obvious.
I'm just saying in general, you've got a category of quote categories and you're mapping to another category of categories.
Oh, I see
So
what you're saying, yeah.
It should have a two structure.
Yes, no, that is, well, I mean, we're mapping from a category of categories, and we're mapping to a category of coalgebras. I'm not.
Yeah, I mean, we call this is called a functor, but it's
It's a
really
pseudo-functor,
the whole thing itself is already like a functor category.
Yeah.
I'll stop causing trouble for the moment.
No, these are good questions. Okay, so this last part is a little bit of a digression from the incrementality, although it is fully compatible with the incrementality stuff. So we kind of this could go. This is sort of an alternative direction with which we can take monoidal grammars. So basically, for a given string of words, not all parse states are equally likely. So can we assign weights and probabilities to parse states and parsings? So the way that we do this is we kind of generalize to semirings rather than just sticking to probabilities and the reals. So we define this S monoidal signature, which is just a monoidal signature equipped with a mapping from our arrows into our semiring. And a S monoidal grammar is just a monoidal grammar that we're building on top of an S monoidal signature, and S monoidal presentation, which is the definition I've skipped here. So we can kind of think of R as mapping parse states and parsings to weights that correspond to their likelihood. And we can characterize any monoidal grammar as the B monoidal grammar where we have R as just a constant function. Oh, I see I've cheated and I've said functor before. I've described it as a functor. It's still a function in this slide.
So this is just saying, yeah, but instead of saying before that, is it possible for this to be grammatical so far you're just extending the true false to a continual probability value?
Yeah, you
Okay.
can. Yeah, that's right.
Okay.
So R is still a function, but I'm going to make it into a functor in a moment. So if we define S to be this trivial monoidal category where our arrows are the elements of S, and both composition and tensor product are semi-ring multiplications. This is a one element or one object category. Then we can just extend R into a functor by just mapping both composition and tensor product to multiplication. And so then this is this kind of nice structure that will we can do some fun things with. So this is now what our morphisms look like. They're no longer just these commuting triangles, but now they're these commuting squares, where we have our where we have to commute along both R and our inclusion maps, like we were doing before. So S-monoidal grammars play nicely with incrementality construction, but we need to switch from non-deterministic automata to weighted automata, which are basically, rather than having this power sets, we're looking at functions from the set into S. And so the incrementality functor maps S-monoidal grammars to coalgebras of the weighted automata functor. So this is the you can develop everything just starting from this rather than starting from the non-deterministic grammars, non-deterministic automata, but I think it's a little bit more intuitive when you go from the other direction. All right, so now the kind of punchline of this and why we even bother with this. So this constraint that R is a functor is a pretty strong constraint, because basically what we're saying is that the weight of a parse state can be expressed as a product of the weights of its components. And this is the rules that are used to construct it. If you think about it from this weighted context-free grammars are a thing. They assign weights to the generating rules. And this is a similar concept. We're defining R based on the weights it assigns to the generating arrows. And so the way now that we can express the weight of a particular parse state is just as a product of the weights of the components generating arrows. And so this product is just because of the fact that we're mapping both composition and tensor products to semi-ring multiplication. And so if we take logs of everything, because we're assuming that we're in R greater than or equal to 0, this reduces to a linear model, which is kind of nice. So that now we have our log of our parse states weights being expressed as a sum of, like a weighted sum of our weights on the individual generating arrows. And the punchline here is we can actually learn this from data or a distribution. So in order to learn this, you need a notion of what is the weight of a parse state. So you need to have some empirical weights for some parse states. In kind of the paper version, we're defining these weights with this notion of a maximal parse state likelihood, where you fix a language model and then you can compute the likelihood that a particular parse state is the most expanded parse state for the set of possible sentences that could finish from some given string of words. And if you do that for some small number of parse states and fit this linear model, you can then model this kind of like a naive Bayes sort of approach for modeling linguistic parsing, so modeling the various distribution of syntactic interpretations of a subsentence. And that's all I've got. Thank you.
questions?
More comment. So I guess this thing of, likelihood of parsing reminds me of the thing, right, that, if you try to apply natural language, a big problem, issue of natural language, well, it's always highly ambiguous, and really when you understand it's because we prune out by saying, yeah, this is grammatical, but it's saying something trivial or irrelevant, and that, and it's part of the idea, maybe this could be a way of describing that process.
So I think that process of like whether or not a sentence is saying something trivial or irrelevant is stepping away from syntax and into semantics.
Well, sure. Well, I guess the thing I have in mind is, maybe in natural language, in theory they're clean cut, in practice they probably aren't, because yes, I could in principle generate all 5 million possible parses and then do it as opposed to, especially this incremental thing, pruning along the way.
Yep. Yeah, so that's very true. This approach allows us to prune along the way, and it allows us to represent a evolving probability distribution upon which we are interpreting the sentence. So there's kind of this canonical sentence, complex houses students, and when that's used to describe this sort of thing. So when you hear, so the phrase in the sentence, complex houses students, complex is a noun, houses is a verb, and students I'm sorry, complex is an adjective. No, complex is.
It's a subject with the noun.
Yeah, exactly. I'm sorry, I've been talking too long. Complex is the noun, houses is the verb, and student is a noun.
Right, well, if I hear complex houses, yes, I have two parses that are viable.
Yeah.
Complex is the adjective modifying house, which is a noun, or complex is the noun that goes with the verb houses.
Yep.
It's only when I get to the third, students, do I...
Exactly. So the idea here is that the incremental construction, when we apply it to this, and we kind of look at what at each step, our state is kind of like, it's not exactly a probability distribution because we're looking at likelihoods rather than probabilities, but it's sort of like a weighted set of our possible parse states. And so after we see complex, we see our parse states are the different interpretation of complex as an adjective or as a noun. Complex houses, now we have the different interpretations of this, but each weighted with their relative likelihood values. Complex houses students, now we are, our weight shifts dramatically in the direction of the correct sentence that we've constructed here.
So, do you have examples, like, I might have missed it here, but, so you started with the sort of the Lembeck style stuff.
Yeah.
Then you said, okay, here's a categorical generalization.
Yep.
Here's how we recover the Lembeck style stuff in the categorical generalization. And here's how we do the categorical generalization as sort of automata, right?
Yeah.
Do you have examples of where this, so what you didn't show is that this categorical generalization has any uses that aren't already captured just by the Lembeck style case.
Yep.
So please, I assume you have some.
Yeah, so I don't have anything off the top of my head. I have, so you can do, you can represent context-free grammars very easily in the Monoidal grammar.
To be a grammar, you already knew how to do that without categories.
Yeah,
right? So
no, absolutely.
You're using all these categories, what are they bringing to the table?
So actually the use of the Monoidal grammar construction was more, rather than the generalization that we have from it, it was more to make it easier to talk about the relationship with coalgebra and to incorporate the vocabulary directly into the category in a way that then allowed the slice construction to give that functor a sort of natural commutativity property. When we're working in pregroups and you're looking at the canonical representation of pregroups as categories and try to extend that to coalgebra, the interaction between the vocabulary and the language itself is kind of tough to work out. So the utility of the Monoidal grammar is really just to separate that out. Whether or not it actually lets us represent far more complex and interesting grammars is an open question. My suspicion is yes, but that wasn't really the focus of this.
Okay, thank you.
I'm sorry,
Yeah.
I may be a bit behind, but with respect to assigning weights, are you learning those weights empirically, or is there some sort of method of inferring them from the sort of syntactical structure?
Yeah, so I left it off the slides because it's really complicated, but it's not complicated, it's just I haven't found a good simple way to explain it.
I'm imagining
The-
almost as though weights could be correlated with like the numbers of maps from a particular interpretation into like and other related interpretations.
And I think that is probably what happens. So the way you have to start from this is to think about what does it mean for a parse state to have a weight? And in order to answer that question, you need to think about, well, what is the distribution by which sentences are produced? There's some notion of, some sentences have multiple parsings, and given some set of words, if we have like 3 words, if we see the words complex houses, if I want to rank and assign a probability to the different possible parsings for complex houses, I need to start with some understanding of the distribution from which the word after complex houses is going to be drawn. And so this is a probabilistic language model. I need to know what is the relative probability of the word after complex houses, or that the complex house is going to end in are ugly versus students. And so in order for me to do that, I need to start with this probability distribution. So once you start with that probability distribution, you can you can work backwards to what the weights of the parse states should be. They should be the sort of probability, they should be this probability that this parse state is going to be the best, so maximal means it can't be expanded anymore, parse state for the most likely sentences that can follow after this. And so this turns into this series of sums, and if you have a parser, you can empirically compute that on a small set of parse states, and then learn the rules from that small set, which will let you get sort of a guess of what it should be for the other ones in this approach.
I mean, when you're doing this, are you like starting with tree banks to start the process out, or are you going directly from free text?
Yeah, really great question. So I haven't actually implemented this yet. That is on my to-do list. My plan is to start with a context-free, like one of the open source complex-free grammar parsers on Project Gutenberg, and then there's the notion that I have for this right now uses this language model, this probability distribution, but that's kind of intractable in general. So there's another stage of approximation upon which we're going to approximate to these probability distributions based on this underlying data that needs to be worked out in order for that to kind of pan out to something that's useful and implementable. Cool. All right, thanks.
All right, thank you very much. Sure, you get it.